Good morning, everybody. Again, this is Dr. Jingbo Louise Liu from Texas A&M University, Kingsville. I'm the organic chemistry instructor for Summer 1 and Summer 2. Today, we are going to discuss our Chapter 9 related to the alkyne. So in this Chapter 9, we are going to show you what's the definition of alkyne, what's the properties of alkynes, carbon hybridization and associated geometry and bonding forces. Also, we are going to name the alkyne, followed by to understand briefly about the physical properties of alkynes. The more important points will be preparation of alkynes and chemical reactions of alkynes. First of all, let's see, what is the alkyne? Alkyne is known as the hydrocarbons with carbon-carbon triple bonds. So hydrocarbons with a carbon-carbon triple bond are known as alkyne. If you have non-cyclic alkyne, the molecular formula will be CnH2n-2. So be advised, whenever you form a double bond between carbons, you are going to lose 2 hydrogens. You form a triple bond, you lose 2 more hydrogens. You form one cyclic single-bonded alkane, you also correspondingly lose 2 hydrogen molecule atoms. So the simplest alkyne is known as acetylene. Acetylene has the formula C2H2. Between carbon and carbon atoms, you form a triple bond. And the compounds with the triple bond at the end of your carbon chain, such as RC, triple bond CH, like this molecule, are monosubstituted. This monosubstituted carbon alkane, hydrocarbon alkane, also called terminal alkane. So again, terminal alkane or monosubstituted alkane has your triple bond at the end of the carbon chain. On the other hand, if you have di-substituted alkane, such as this particular molecule, this carbon triple bond is located in the internal, so you call the internal triple bond or triple bonds. So this is about some important brief introduction of your alkyne. So what are the sources of alkyne? Can be naturally occurring, can be produced by our chemical reactions. So let's trace back to the 19th century. In the late 19th century, so what happened? People using heating the coke and limestone at very high temperature, such as 1800 to 2100 Celsius, you produce calcium carbide and carbon monoxide. This calcium carbide is going to be hydrolyzed to produce acetylene and calcium hydroxide. So that's our production from the limestone and also the coke. And if you produce alkyne, you can use dehydrogenation of your isolene. In this case, you have your isolene, which has a double bond. You are going to heat it up again to produce alkyne, produce another molecule of hydrogen molecule. So this reaction usually is an exothermic reaction. You need to heat it up in a very high temperature in order to convert isolene to the alkyne, acetylene in this case, and hydrogen molecule. Sometimes if you have enzymes, you can use this enzyme to catalyze some chemical reaction, such as one of the reaction called acetylenases. This reaction occurs which convert particularly a double bond to single bond. So this reaction is highly selective reaction. So naturally occurring alkyne can be, at these examples, the first one is this called dinesamine. Dinesamine A can be produced by some bacteria. So you can see this molecule, This one can have some capability to cleavage some DNAs. Another molecule is called diacetylene. So this diacetylene has been identified as a component in the atmosphere of the Pluto or Neptune. And some other compounds related to the triple bonds, such as in the fatty acid compounds, you may compose of this alkene triple bonded carbons, such as this stearic acid. And about the nomenclature of the alkene, so essentially you based on the corresponding alkane. So single bonded hydrocarbons. So you simply replace the ANE suffix to the YNE suffix. For example, if we have this 1, 2, 3 carbons, you call it propane. Change propane ANE to propine. Change A to Y. So if I have my butane, so the second molecule called 1-butane. The third molecule, you have 4 carbons, so you have the triple bonded carbon located in number 2 and number 3. So this case you call 2-butane. If you have the other molecule a little more complicated, so you count the carbon with the triple bonded carbon located in the smallest locand. In this case, the last molecule you called 4,4-dimethyl 2-pentane. So this is the simple molecule. If you have the molecules which are slightly complicated, such as you have alkene and also alkyne, how you are going to name it? The name will be essentially combined alkene and alkyne. You call it alkene. In this case, this alkene has the lower priority compared with alkyne. You name it essentially as your alkyne, but this alkene will be your substituents, and you need to identify the double bond and triple bond. In this molecule, you totally have 7 carbons. Your double bond located in number 1, you call the hept1 in 5 ions. This is your alkyne. So that's how you name it if it becomes complicated. The physical properties of most of the alkynes, they are essentially resemble to the alkane and alkene, meaning the alkane, and alkyne, as long as they have a similar number of carbons, they have very similar physical properties, such as the density are very low, such as the water solubility is also very low. Boiling points are very similar to the corresponding alkane. Again, your alkane, alkyne, and alkene, they have very similar boiling points. Another point about this alkyne will be structure and bondings. Your acetylene, you have C2H2. This molecule is a linear molecule, meaning you are going to form a triple bond between carbon-carbon. The carbon-carbon triple bonds has the length 120 picometers. Carbon-hydrogen bond is 106. Compared with the double bond, single bond, you see triple bond is shortened. Carbon-hydrogen bond in the triple bonded compounds also being shortened. Later on, you find that the bond strength has been also strengthened. If you have the cycloalkane will subject to the strain involved in spatial hindrance and also torsional strains. Both of them will be involved in. So the smallest cycloalkane possibly composed of 9 different carbons, as we showed in this molecule. So you can see the molecule is obviously going to be subjected to the band, including the triple bonded carbon. So this part, this 2 carbon, triple bonded carbon bonded with 2 more carbons. So you see the band occurring. In terms of the alkyne bonding, so you need to know this carbons is going to take sp hybridization. So you are going to form 2 pi bonds and 1 sigma bond. The pi bonds are formed due to the overlap of your py and pz, and your sigma bond is formed due to the sp hybrid orbital with the other sp hybrid orbitals. This diagram essentially showed you this is a sigma bond. These two are considered pi bonds. And also from these electrostatic potential maps, so you can see the triple bonded carbon have very high electron density. So you use red to represent it. So indicating the chemical reactive sites will be triple bonded carbon. So this table 9.1 summarizes the name, molecular formula, structural formula, bond length, bond distance, bond angle, hybridization, and S characterization of the alkene, alkyne, and alkane. Alkane such as ethane, alkene such as ethylene or ethane, alkyne such as acetylene and ethine. These 3 different molecules are commonly used for us to understand their structures, the bond lengths, bond distances between carbon-carbon, between carbon hydrogens, as you see in the single bonds. So carbon-carbon bond is longer. Carbon-hydrogen bond also longer. Carbon double bond you can see obviously decreased, including carbon-hydrogen bonds also decreased. Triple bond you can see the obvious decrease in both carbon-carbon triple bonds and carbon-hydrogen single bonds. And about the bond carbon and carbon-hydrogen bonds, so you can see the different bond angles for this ethane in this molecule. You essentially form a pseudo tetrahedral structure. Carbon-carbon and carbon-hydrogen bond, carbon-carbon, carbon-hydrogen bond, slightly bigger than 109. Carbon-hydrogen, carbon-carbon bond, bigger than 120 in your ethane, which is similar to a trigonal planar structure. For your carbon triple bonds, carbon-carbon, carbon-hydrogen bond, because it's straight line, it's linear structure, you are going to see 180 degree. Carbon triple bond, double bond, single bond, you can find the bond strengths based on the carbon-carbon bond dissociation enthalpy. So what you see for the single bond, 390, double bond 720. Over here, be careful. Double bond, the bond strength is not twice of the single bond strength, meaning the pi bond is weaker than the sigma bond. Similarly, your triple bond, you can see this dissociation enthalpy. So 960 is not the triple of 375. Again, confirmed the pi bond is weaker than the sigma bond. About hybridization of the different of the carbon in the different alkane, alkyne, and alkene. So you take sp3, sp2, and sp. And for the S characters, you have 25, 33, 50% respectively. From this point, we also need to know the pKa, which corresponding to your acidities. If you have your hydrogens involved in your hydrocarbons, that hydrogen may be donated. In this case, you consider a very weak acidity of your hydrocarbons. So the bonding in the alkane, alkyne, and alkene also summarized in this slide. Essentially, what you can see, from your ethane to ethylene, acetylene, what you see, your structure or your geometry of your carbon changed from your tetrahedral to trigonal planar to the linear structure. Your carbon-carbon, carbon-hydrogen bonds becomes shorter and shorter, stronger and stronger. The acidity of carbon-hydrogen bonds so becomes stronger, stronger, and stronger, meaning this acetylene tends to produce or donate protons much easier compared with isolene. And also the bond length, as we mentioned, becomes shorter and shorter. Give you some examples for you to study. About the acidity of hydrocarbons, so you can use again the pKa to denote it. If you have the very high pKa, such as in methane, pKa is 60, meaning this methane barely donates proton to produce called methanide, negatively charged anion. This is called carboanions. This is very rarely to be produced, meaning this methane can show a very, very strong weak acid properties. About the acidity trend, usually here is our rule. With the S character decreases, you decrease S character, so your S character, which is 25% all the way to 50%, your pKa will become smaller. From your alkane to alkene to alkyne, you see your pKa from 62 to 45 to 26, meaning the acidity increases. Whenever you have a smaller acidity, so that pKa will be bigger, such as methane, ethane or methane, they have more than 60. Your isolene is 45, your acetylene, so which is 26. The last molecule is a stronger acid compared with the other ones. If you have this alkyne, you're subjected to the terminal mono substitution. So this substituted alkyne also produces proton much more easier than the related alkene and alkyne. So pKa is 25.5. Again, it's generally speaking is a very weak acid. So if you have water reacted with this acetylene, so you can produce acetylide. So this negatively charged ion you call acetylide, negative ions. However, the forward reaction is very, very unfavorable, meaning this deprotonation of your acetylene to produce acetylide is not favorable. This acetylide, when you form the negatively charged ions, meaning your carbon is going to have a lone pair which located in your sp hybrid orbital. So about the acid-base reaction, you can consider this way. Consider your alkyne, such as your acetylene, as a weak acid. You have a base, acid-base, Brownish-Lowry acid, Brownish-Lowry base, they can react. If you have sodium hydroxide, as example, this sodium hydroxide in this case acting as a weak base. This weak acid, weak base, they are not favorable to the forward reaction, meaning when you produce this acetylide anion, carboanion, this reaction barely occurs. So forward reaction is not favorable. Your reverse reaction to the left hand side is favorable. In this case, you need some strong base, such as your imide. If you dissolve metal from the first group, such as sodium, in the liquid ammonia, you are going to produce an imide. This imide is a pretty strong base. In this case, your acetylene can react with strong base, so going to the reaction to the forward. So compared with your ammonia, so your acetylene is a stronger acid than the ammonia. Your imide is a stronger base compared with your acetylide anion. Therefore, strong acid, strong Brownish-Lowry acid, strong Brownish-Lowry base will react. Reaction move to the forward to produce this acetylide. This negatively charged ions is very important for this chapter. We are going to use this one for our alkylation reaction. You are going to learn electron transfer, proton transfer, electron transfer, proton transfer, again, this new mechanism. So this is essentially about the properties about alkyne and the nomenclature. This alkyne can be prepared by different approaches. The first approach called alkylation, meaning if you have your say acetylene-based compounds, so you are going to subject it to the addition reaction. If you have methyl or primary alkyl halides, you are going to produce a substituted alkyne. This example is, so you have acetylide and ion reacted with your primary alkyl compounds. These will be bonded with your carbon from your triple bonded compounds. Sodium and halides, they produce sodium halides. This reaction is going through as an SN2 reaction, meaning this acetylide is more attracted to the alkyl group in your halides. This carbon halides bond subjected to the heterolytic bond cleavage. So again, you form your sodium chloride or sodium halides. Sodium chloride or this chloride-based compound is more commonly used, or bromide or chloride are commonly used compounds. For example, so if I have my acetylene, I want to produce, from my acetylene, I want to produce 2-pentyne. What happened? You originally have 2 carbons. Pentyne, you have 5 carbons. How do you add in 5 carbons? So in this case, you see, you have from my right-hand side carbon, this hydrogen has been replaced by a methyl group. The left-hand side carbon, this hydrogen, replaced it by an iso group. What you are going to do? You need to go through 2 steps. First step, you may add in an iso group to the terminal carbon. How do you do this? You are going to use a very strong base, such as you dissolve sodium into the ammonia. You form this sodium imide, which is very strong base, and you react it with isobromide. So this reaction, you call it alkylation. This alkylation allows you to add in CH2, CH3 to your terminal carbon. Therefore, you form a butane. Similarly, you add in 1 more carbon under the sodium imide in the liquid ammonia. You add methyl bromide. Therefore, the second terminal carbon will be bonded with your methyl group. This reaction gives you very high product yield. 81% of your 2-pentane will be produced. So here you have this sodium imide ammonia. This is your condition. This represents the reagents. You write it down either above your reaction arrow or below your reaction arrow. So that's how you are going to do it. First of all, this first step, you form this negatively charged intermediate acetylide. And then second step, you are going to add in different functional groups. So in the first reaction, acetylene is protonated with sodium imide in the ammonia, and then this acetylide reacted with your iso group from your isobromide. And then second step, this butane is going to subject to the also the deprotonation of the second hydrogen, and then in the sodium imide ammonia condition, and then this negatively charged ion is going to react with your methyl group to produce a final product. There's 2 different reactants. And also, in order to produce your alkyne, you also can use elimination reaction. If you have acetylide and ion, you are going to react it with halides. Those alcohol halides, they are not primary halides. They are secondary or tertiary halides. What's going to happen? This secondary or tertiary halides, for example, this terbutyl bromide is going to subject to the elimination reaction. So what happened? This hydrogen is going to be attracted by the carbon from your acetylide. You produce acetylene, and then this bromide, you remove HBr, you remove this Br, technically speaking, you produce a propane. That's another reaction related to this acetylide. So you can involve in the elimination reaction of your tertiary or secondary halides to produce alkene. Another reaction related to production of your alkyne, so you can do the double dehydrohalogenation of your dihalides. Dihalides, you can have two types. One type you call the germinal halides. These germinal dihalides related to the halides atom connected or bonded to the same carbon. Your vicinal dihalides related to the two halide atoms connected to two different carbons. In this case, under the sodium amide in liquid nitrogen, so you are going to produce alkyne and through alkene and then further to the alkyne. This is called the double dehydrohalogenation. You remove halides. For example, if I have this 1,1-dichloro-3,3-dimethylbutane under sodium amide in liquid ammonia, you are going to produce these alkyne products. So you form this kind of sodium salt of your alkyne. This molecule is going to be further subjected to the hydrolysis to produce butane, 3,3-dimethylbutane. Another example, if I have this dihalides, this is first one is a germinal, second one terminal halides. So you also go through similar reaction procedures under the sodium amide in liquid nitrogen. Again, you are going to produce this final product. Both what you see, both products are the terminal alkyne. So three equivalent of the bases are required if the alkyne is terminal. Since the terminal alkyne subject to the deprotonation by the base as soon as it formed, you want to produce a terminal alkyne, you can go through double dehydrohalogenation. You can do this dehydrohalogenation of the dihalides which are germinal or dihalides which can be vicinal. So this is about dehydrohalogenation. Another formation of your alkyne can be from alkene. So what you can do, you are going to produce vicinal dihalides from your alkene. You have carbon-carbon double bonds. You are going to go through the halogenation, such as bromination. You are going to form a vicinal dihalides. You form 1,1-dibromo-3-methyl, so butane, and then you go through ammonia, sodium amide in liquid ammonia, and then you are going to go through the water. So you produce this 3-methyl-1-butane. This is another one to produce alkane. So you can go through several different methods. Let me briefly summarize how you are going to produce your alkene. The first one is the reaction through the alkylation. Alkylation produces alkyne with the enlarged carbon chain. Carbon numbers will be increased. And also you can prepare the alkene from the elimination reaction, such as from dehydrogenation reaction. Also, you can produce alkyne from alkene through two different steps. First of all, alkene is going to be subject to the halogenation, such as bromination, and then you are going to go through the dehalogenation reaction of this vinyl dihalides. You are going to produce this alkyne. There's different types of productions of alkyne. I'm going to take a 5 minutes break, and then we are going to continue the different chemical reactions of alkyne. So generally speaking, we are going to study alkylation reaction you already learned. Also, we are going to learn hydrogenation reactions, hydration reaction, hydrohalogenation reaction, halogenation reaction, and also ozonolysis. And then the very last one, we are going to study retrosynthesis to the different compounds using acetylide. So that's it for now. We are going to have a 5 minutes break, and then we come back to continue the following sections about reactions of alkyne carbon triple bonds. Thank you. You have a good day.